Hi, so today we're gonna be talking about electric potential. So, what is electric potential? Electric potential is the idea that charges in an electric field store potential energy. So, right now we have this little charge, right? This charge has a charge of plus Q. So we know that the electric field for a plus Q charge is equal to Q over 4 pi epsilon naught, and then we have r squared, right? Where r is a distance away from the center of the charge to another charge or something. Okay. But we also know that with the electric field, we also have the electric force, right? We know that force, let's say I bring another charge here, plus Q, right? The force acting on this charge is F of C is equal to Q times 4 pi epsilon naught r squared, or just, Q squared over 4 pi epsilon naught r squared. So this charge right here is experiencing a force in this direction from this charge right here. And the value of that force, the magnitude, is this, Q squared 4 pi epsilon naught over r squared. Okay, so we understand that there's a force and then there's also the electric field. So what is the electric potential? Well, the electric potential is the idea that, let's say I let this system go from rest, right? What's going to happen to this charge? What's going to happen, right? So what's actually going to happen is, let's say this charge stays in place. This charge is going to stay in place. And then this charge, what's going to happen is this charge starts moving at a speed, right? Because it's getting pushed away by the force from this charge. So then if I let this system go from rest, it starts moving from here and it just starts moving at a speed. It accelerates. So the idea of the electric potential is, we know that when we let this charge go from rest, it'll move at a certain speed. At the instant I let it go from rest, it's going to move at a certain speed. The idea is how much. What is that speed? And we get that from converting the electric potential energy from based on the position of the charges to the kinetic energy it has. But how will we derive something like that? So we know that for electric potential energy, or energy in this case, energy usually comes from the work energy theorem. And what the work energy theorem is, it's the idea of this. We know that work is equal to the integral of the force times with the dot product of the displacement, right? So this charge is going to move a certain distance, right? Let's say, and this has direction, right? So we'll say that this way is positive, this way is negative, right? So we know that the work done on this charge by the force from this charge is based on the magnitude of the force times the magnitude of the force times the displacement times the cosine of theta, or cosine of theta. So basically, how much of this force is in the direction that the charge travels. So let's say the charge travels a distance this way. Let's say it travels a distance d away from here, right? Then the work is how much of the force pushes that q in the direction of d. All right, and that's all well good. So for charges, how does this theorem actually look? Well, for charges, we don't really want to use the force, right? We like using the electric field. So a way to actually rewrite this is the work is equal to, well, what is the force, right? It's Q times 4 pi epsilon naught r squared with respect to dr, and then cosine theta. And in this case, cosine theta is going to be, well, theta is going to be, 0. So cosine of 0 is, this just goes to 1. So honestly, just remember that this is based on the direction of how much the force is aligned with the displacement. So just remember to take that into consideration. But right now, we'll just leave that there. So now what I'm going to do is I'm going to take away this q because it's a constant, one of the q's, and I'm going to put it outside the integral, and then I'm going to write it like this. 4 pi epsilon naught r squared dr, right? So do you guys notice anything about this, what this term looks like? Well, we know that this is just the electric field, right? So we can just write this as q e dr, all right? But the one thing that's very important, and I think gets a lot of people confused, is the idea that this work will provide a positive answer. But this work necessarily, this idea of work, isn't technically the potential, the energy the charge has, right? We know that work is equal to negative potential energy, right? So then let's say I wanted to rewrite this. Well, then if I wanted to write it in terms of U, that would equal negative work, which would equal negative Q, or actually I'll write it like this, Q E D R. So this is the negative, not the next, sorry, this is the potential energy that charges will score. This is how we derive the potential energy that charges have in an electric field. Okay, but the idea of the electric potential is a little different. This is known as electric potential energy. But electric potential is this part, right? What it actually is change in V is equal to the negative E dot dr. That's what this is, or electric potential difference. And I'll explain why it's also called difference, right? So the idea of how I like to think about it is, let's say I bring a charge from infinity, right? Let's say this is infinity, right? This is infinity, all the way to this distance right here, which is r away from this q, right? Actually, I'll write it over here. It's a little easier. So this is my q plus right here, and I bring a charge from infinity all the way to this spot right here, plus q, right? Which is a distance d away, okay? Now, we know that this charge is repelling this charge away, right? Because it's like charges, so it's repelling it away. So the work that I had to do to bring this charge from infinity to here is negative work, right? Because I'm working against an electric field. That's what it looks like. So if I want to know the potential energy stored from here, it would be U is equal to QV, right? Because that's our potential energy, right? That's what this is, right? So U is equal to Q times the negative electric field dr. Okay? So now we have this integral. And we also know that the electric field is based on this charge right here, the plus q, or this q as well. And we can write that as, q, negative q, k over 4 pi epsilon naught r squared dr. Okay, now we want to integrate this, but first we have to define our limits. So what is our limits? Well, what was our starting position? Our starting position was all the way from infinity. Starting position was all the way from infinity, and then we wanted to come to this spot right here, which is distance d away. So then our ending spot is going to be d. So now let's actually integrate this. We know that we can take out all our constants, right? So negative q, or in this case, sorry, this would just be q times 4 pi epsilon naught over 1 over r squared. These are all our constants right here that we can pull out because they don't change. But the one thing that does change is r, as we move along in space. So now let's integrate this. Well, we know that r squared, 1 over r squared is equal to r to the negative squared. So then using our integral rule for polynomials, we know that r to the negative 2 plus 1 divided by negative 2 plus 1. So this is going to be negative 1 times r to the negative 1 power. So that would just look like negative 1 over r, right? Okay, we got that there. So now, well, I have no room. Okay, let's go this way. Now, let's just move this along this way, and we'll just plug that in. So negative q squared over 4 pi epsilon naught times 1 over negative r from r to infinity, right? Because that cancels it. Yeah, now we're good. Q squared over 4 pi epsilon naught times 1 over infinity, 1 over r minus 1 over infinity. Sorry, I was getting a little confused with the signs, but it's good to think about it. So we know that anything to the infinity, 1 over infinity power, well, this is just going to go to 0, right? This is just going to go to 0. And then if I do this here, we get, this is q squared over 4 pi epsilon naught times r. This is the value for the electric potential energy. Potential energy in a electric field consisting of one charge. Now let's say I just wanted to find the electric potential. Well, the electric potential, we already have it. It's right here. All the electric potential is just the negative E dot dr. It's this part right here. So if I just wanted to determine the electric potential, all I had to do is divide out a Q, right? Because there's no more Q. Because V is equal to the electric potential energy divided by Q. That's all it is. It's like the electric field. We know that the electric field is just, if I have this charge right here, the electric field tells me how strong the electric force will be at certain points in space, but based on the charge I placed there. But we haven't placed a charge. That's all it is. The electric field tells me how strong a force will be if a certain charge was placed there. And it's the same thing for electric potential. How much energy will a charged particle have in this point in space if I was to place a charged particle there? So if I actually divide out Q here, if I take the electric potential, V is equal to Q squared over 4 pi epsilon naught r, and I divided it by Q, right? We get V is equal to Q squared over 4 pi epsilon naught r times 1 over Q. 1 cancels out, and this is the electric potential energy for a point charge. That's what this is. Electric potential energy for a point charge. We did it. Yay. Basically, that's the idea. So just to recap, the idea of the electric potential is if I bring a charge all the way from infinity to this distance right here, which is the distance r away, right? How much electric potential energy could it have if a charge was placed right here, right? Because right now, I'm dealing only with space. That's what I'm dealing with. I'm dealing with the idea of space. The electric field distorts space. And so the electric potential measures it measures the energy a charged particle could have in that distorted space at certain points, right? So from infinity to r, if I brought a charge here, let's say the charge value was 2q, right? It's going to have an electric potential energy of, we know that U is equal to Q times V. And we know that V is just the electric potential. The electric potential for a point charge is just this. So it's going to be 2Q times Q over 4 pi epsilon naught R. So this is the electric potential energy it will have. 2 squared over 4 pi epsilon naught R. And if I brought a charge of 3Q, then it's going to be U is equal to 3Q squared over 4 pi epsilon naught R. But these both all have the same potential. They all have the same potential, right? The only thing that changed was the charge, the value of the charge they had. But their electric potential is still, for a point charge, is Q over 4 pi epsilon naught R. That's all it is. All right, thank you for watching. Hope you guys have a great day.